Oh. All right. Hello again. Welcome to lecture 22. So I put an iClicker question is on this whiteboard, and as far as the last time I checked, it's about 50-50. So I give you a few more minutes to do it, and while waiting for those students who come just on time, we can talk briefly about exam 2. So there are about more than 10 people who haven't taken the exam. So we cannot discuss the answers, definitely. But I can share a few things that I have in mind. One is the average before adjustment is 73%, which which increased from the first exam. The first exam, the average was 55. So keep up the excellent work. This shows that physics is easy. You can do it, right? Second, despite some of you think that you are in jail with me, second, 73% is before correction. So your score is basically that number, 73% times, basically, no, times 15 divided by 14. So this is the real score. So the average score is, so if this is the average, which is 73% times 15 divided by 14, because you only need to get 14 in order to get a perfect score, then this is about 78%. Okay. So you will not see, okay, this is important, because I know some of you will send me this email. You will not see the correction on Canvas, okay? You have been through this before. It has been corrected on my gradebook, which I will share this weekend. I try to share my gradebook with you once a week, okay? Good? Any question? So, great. So before we continue, let's recap. Last time we discussed about mutual inductance. So basically mutual inductance, you need two coils. So I have a demo for you. So we have these two coils, and let's say this one is primary, and this one is secondary, okay? And what we, based on Faraday's law, well, based on all physics, but mostly Faraday's law and Lenz's law, we claim or we study that we can transfer energy. And this is one demonstration of mutual inductance. So we have two coils, and one thing, one thing that produce, and then on top of that, we need alternating currents. And this keyboard is a good source of alternating currents, because in order to produce certain tune, it requires to oscillate with a defined frequency, okay? So right now, if I have a good distance between these two coils, there is not much energy transfer. And also there is not much energy transfer. So, sorry, it worked before. So basically, if the distance is long, then the energy transfer becomes less efficient. When I bring the two coils closer to each other, I hope you can hear, there is some energy transfer. If I put materials in it, similar to iron core in the transformator, in a transformers, then the energy transfer is more efficient. Okay? So this is just a standard demo. So that's one demo. Another thing that we studied last time, okay, first we need AC. And we briefly discussed about the war of currents. So AC, Nikola Tesla was the person that get credited with with making AC popular, that survived until now. So for mutual inductance, we need AC. And AC is useful in making a transformer. And because of that, AC wins. Okay, AC stands for alternating currents. Okay, so we need AC, we need transformers. So back to the iClicker. So the answer is, so this is a picture from the lecture notes that I posted this morning. So basically we have a power plant on the left and then step up transformer. So basically the step up transformer will increase. So we have, let's say, this transformer here. Okay. Step up transformer will increase EMF by the ratio of the number of coils. So E1, EMF 1 divided by N1 is equal to EMF 2 divided by N2. And of course, you can rearrange this equation whatever you want. You can write it like this. Basically, the EMF is proportional to the number of turns. And we did this last time. Okay. So another reason, one reason why AC wins one is that it turns out that many ways to generate electricity involve rotary motion, like wind turbine, water turbines. So that itself fluctuate the currents from positive to negative, positive and negative. So AC is convenient. But another thing that is important is that it turns out that in order for transferring electricity over a long distance, it's better to do that at a high voltage. This is why you see all those signs near power lines. Okay. So the story was actually Edison was the one. Edison hired Tesla at the end of maybe around 1880-ish. So Edison recognized that Tesla is really bright. In addition to a good physicist, Tesla also can speak more than 10 languages. So, so we will go through that slide. So basically, if you have a electric generator, such as using a water turbine, the thing that you generate has a defined power. Basically, the energy of, let's say, a waterfall. So I call this P generator. And at this time, you know that P, or the power, is equal to voltage times the currents. The only thing that a generator has or given is the power. Okay. So that's one. So you know P is equal to P generator is equal to V times I. Power lines is basically cables. So, and when you transfer electricity, there is a joule heating. So the P, I guess, loss of power lines is also V times I. And you can tweak V and I here. But for a cable, all you know is a resistor. So the resistor is given here based on the material, the length, the radius. So you get this. And you can express, so basically this is the next slide. And V, because we want to invoke I, so V is equal to I times R. Then this expression becomes I square times R. Okay. So, and then this current is the same as this current because this is the one that you want to transfer. So this I here is equal to, using the equation on the top, is equal to I is equal to P generator divided by the voltage that you want. Okay. Or you can just do this. Okay. I. And this one becomes P generator generator divided by V times R. So you know what P is, which is the power, the energy per unit time of, let's say, a waterfall, and radius is the property of the cable. Then all you need is to tweak V, right? So this expression shows that the higher the potential, the higher the voltage, the lower the power loss. So this is why for power lines, they want to increase the voltage to 1,000,000 volt, basically, on the order of 1,000,000 volt. Okay. So in real life, the reason why we have an efficient electrical or AC civilization is that we have a step up generator here. So at this point, the voltage is on the order of 1,000,000 volts. And then we have a step down potential here. And then please check. On Monday, I say that the potential is 110. Maybe the correct number is 120. 110 is in Indonesia. Any question? Good. I hope that helps. Next, what we want to discuss is an inductor. So we learned about a capacitor before, which is a device that can save energy in terms of charge. And we learned about a resistor. Let's see, a resistor, which is a device that modulates voltage or slows down currents. Right now, what we want to study is an inductor. There is a different symbol of inductor than this, but let's, and also for resistor, there some books draw it like that, but we can just use this symbol for now. And for capacitor, make sure that the length of the two lines are the same. Okay, so C, R, L. So what is an inductor? Anyone knows? Anyone wants to help? No? Okay, so inductor is basically you have a coil. It has something to do with mutual inductance, but with one coil. So instead of mutual inductance, we call it self-inductance. And then from Wednesday, this is from Wednesday. Sorry, from Monday. So I will be sleep deprived until early April. So if I misspeak or misspoke, you have to correct me. Okay. So from Monday, M is equal to, this is mutual inductance, is equal to N1, N2 times mu naught, I think A divided by L. So this one, on Monday, we discussed communication between two coils. But right now, we only study one coil. One coil. And here, you still have to supply AC currents. Okay, this is AC. This is the symbol for AC power supply. So it turns out that everything that we did on Monday applies, but the changing magnetic flux can affect itself. I don't know what is a good analogy? Basically, you try to, maybe if you can come up with some analogy, you can share it with me. Basically, because the input alternates between positive and negatives, that's literally what AC current is. The flux that it produces also fluctuates. And because this inductor itself is a coil, it affects the inductor. So the primary coil is also the secondary coil here. So basically all the things that we discussed still the same, which is, let's say, instead of the flux from a different coil, I think the symbol that I use is self magnetic flux, which is B times A, okay? And then what is the magnetic field of a solenoid? Well, okay. It's just a test in case you already forget. Okay. And then what else? And here is equal to number of turns divided by the length. So it's a function of length also. So N is the total number of turn and L is the total length. And then basically for the EMF, for mutual inductance, I'm gonna write and then I'm gonna erase, okay? For mutual inductance, the induced EMF is N times due to the other coil. So N times the change of flux, and then which we set to be M. I think on Monday I ignore the negative signs because the current goes from positive, negative, and positive and negative. This is the definition of mutual inductance. But since this is only one coil, then we use a different symbol, which is L. L is the inductance or the self-inductance. So I have this problem on the lecture notes. So if we have a coil, what is the self-inductance? And I derive it a little bit longer way, which you can read by yourself. But since we have this, somehow I wrote the equation here. So let's just use this equation. So what is this problem? So this is not iClicker, by the way. This is how I write my lecture notes. There are so many shortcuts. For some reason, I chose iClicker shortcut. So the question here is calculate the self-inductance L, this L here, of a solenoid with N turns and of length L. So you can use the expression that, I don't know, Holden or Nathan or Alan, is that your name? Alex, sorry. Or you can use this equation here. Okay. So for two coils, M is equal to N1 and 2 times mu naught A divided by L. N1 is the number of turns of coil 1. N2 is the number of, not the number of coil, the number of turns of coil 1. And 2 is the number of turns of coil 2. Area is the area of the coil, and L is the length of the coil. So since we have this equation, and also it's good to show you that we can arrive to the same equation using multiple approaches, let's calculate L. So what is N1 for single coil? Single coil with N turns. What is N1 here? What is N2? What is N1 here? N, good. What is N2? Only one coil. Same. Okay, good. So this N1 and times N2 is equal to N squared. And then the rest is the same, right? Mu naught A times L. So let's see if we arrive at the same expression. Any question? Clear? Excellent. We're running out of time. I'm just going to give you some formula, if you don't mind. The next thing that your textbook covers is the energy. The symbol of energy is U, which is equal to 1/2 times L times I square. Okay. So what is this energy? This is the energy that an inductor can store. So capacitor store energy in the context of as a function of charge or potential. The inductor store energy as a function of change of charge. Okay. You can view this, maybe, I don't know, maybe I overuse a mechanical analog too much, like mass and spring. Mass resists velocity and spring resists displacement. So similarly, here, capacitor resists charge and an inductor resists change of charge, which is the currents. Okay. Anyone recognize this formula? Yeah, Minoru. Meaning like what? This is actually a nice formula. People at the back. Let's see, I think 7 is the way to go. Anyone recognize this, the form of this formula? Fatima. There is no Fatima here. Ahmed. Fatima. No, the other Fatima. No, you. We only have one Fatima. Huh? So this formula is nice because it turns out that in nature, this is a generic form of energy. And you've seen this many, many times, right? You've seen this many, many times. For example, 1/2 mv square, 1/2 kx square, 1/2, what else? cv square, and on and on and on. I think when we discuss capacitor, we discuss something like this. So this is really common in nature. It's basically 1/2 times the constant of the system, in this case, a coil, times a variable. And there is a nice theory if you want to calculate the average of certain terms, like this. This is a symbol of average. And the energy is 1/2 times the constants times a variable square. And that relates to definition of temperature, which is a beautiful theory derived by Maxwell. Unfortunately, as you chose, as you physics, skip thermodynamics for pre-meds. So this is the energy. I'm not gonna ask you this on the exam, right? But for energy that an inductor can store is given by U, and this is a capital U. I don't know how to make it clear. So this is a capital U. There is a nice formula, and this is, I was really impressed when I first learned about this formula. So capital U is the energy, but the energy per unit volume, you can use V or use, I think I use V. I need to use volume because voltage is also V. This one is equal to, okay. So because of the, in the interest of time, I want you guys to see the right panel or the right screen. So basically, if you use the expression for self-inductance, which is mu naught times n squared divided by L times A times I squared. So you put L, you put this expression here, and you use A times L, the area times the length as the volume, then U, the capital U, becomes 1/2 B squared divided by mu naught. Or if you are a big fan of a constant, you can write this times B squared, and then times A times L divided by volume. Since A times L, the area times length is volume, then they cancel each other, and you get 1/2 mu naught B squared. Okay. And this is a famous formula for the energy per unit volume. So if you have a magnetic field, so realize in this expression, one thing that amazed me when I first studied this expression is that we derive the expression using an inductor, but the final expression doesn't have anything to do with inductor, meaning as long as you have a magnetic field, there is energy in that volume. And we will use this formula when we discuss about electromagnetic radiation today. And this is, and you can compare this with the energy of a volume that contains an electric field, which is epsilon naught divided by 2 times E squared. Okay. Any questions? All right, so what is the current time? So 40 minutes. So it was a little bit intense. The lecture, I know I went really fast. Let's slow down a little bit. So I can tell you a little bit story about lights. I like this picture. Unfortunately, I cannot zoom this. Can I zoom this? I cannot zoom the picture. So the picture on the right is the picture of Galileo. Anyone a fan of Galileo? He's a cool guy. On the left is Al-Hazan or Ibn al-Haytham. I'm a big fan of al-Haytham. I named my son after him. And I named my daughter after my PhD advisor, which is also an optics genius. So my daughter's name is Biruni. We will talk about Ibn al-Haytham or al-Hazan. So in the context of speed of light or lights, right now we're transitioning to inductance to optics. But today's lecture and Friday's lecture will be on electromagnetic wave. All right, okay. So one thing that, so I'm a big fan of history, including science, history of science. So the first, anyone knows who first measured the speed of light? Huh? Who? Maxwell is good. Maxwell actually derived it. Huh? Oh, Romer? Okay, good. So you read a lot, which is good. The first one who measured the speed of light successfully is Romer. He's a Dane or Danish physicist. But the first failed attempt was done by Galileo. So Galileo, what he did is and I'm not gonna ask you history of science in the exam. So this is just, treat this like, I don't know, piano lesson or something. So you can have a nice conversation during parties. So what he did is he asked his apprentice, who knows, maybe an undergrad, to go to one hill, and another one, perhaps himself, to another hill, and they are quite far. Okay. So what he wanted to measure is the speed of light. Speed of light in physics, we use the symbol c. So before Romer, speed of light was considered to be infinity. It makes sense. You light a candle and you see it immediately. So what happened when he did? So what they did is one has a lantern, okay, and then the plan is if one open a lantern, after the second person see the lantern, he will also open the lantern. And then, so after the person, which is person A, open a lantern, he count time until he sees light from the other hill. Okay? So you have distance, you know the distance, and you can measure time. Do you know how they measure time? Any guess? This is before atomic clock, before iPhone. They use their heartbeat. So, and then they get a number. And then they're good scientists. Galileo is a smart man, first-class scientist. And then he tried to see whether the number makes sense. So he did a control experiment. So what he did is these two people, they go to a house in the same room and they repeat the experiment and they get the same number. So it turns out that what they measure is not the speed of light, but so if you change the distance and run an experiment, and then you shrink the distance by many orders of magnitude and you still get the same number, then what you measure is what? Speed of light or not? What did he really measure? You guys are quiet today. All right, somebody with a hat, a navy hat, sorry, what is that? Patagonia hat. Somebody that is smiling. Sorry, it's me. So what he measured is a human response, like your nervous system, how fast your brain process information. In the interest of time, I'm gonna ask you to read or perhaps watch YouTube videos about all Romer because it's fairly complex. So what he realized is that the time between first, many planets have many moons. Jupiter, one of the moons of Jupiter is Io or Io, and Io or Io revolve around Jupiter, and both of them revolve around the sun. And from that, he could see an eclipse. And all Romer realized that the time between eclipse changes throughout the year, and he hypothesized it was because the distance between Jupiter and Earth changes throughout the year. And since he knows the difference of the distance, and he measured the time difference between different eclipses, he could measure the speed of light by, I think, about a factor of 2, which is quite remarkable. Okay. But the first person who, I think Holden's guess was really good. The first person that not measure but calculate the speed of light to be exactly correct is Maxwell. Okay, so Maxwell. So in the class, I mentioned stories about Faraday. Faraday is a simple man, really hardworking. Like many successful scientists, most of them are very hardworking. But he didn't have like Cambridge, Edinburgh, Oxford training. But Maxwell has a good mathematical understanding. So both of them, they chat, and Maxwell realized that if there is basically Faraday came up with a hypothesis that, well, at least from what I read, that light is an electromagnetic wave that perturbs space. And Maxwell did the math, and he said that thing can only be true if the speed of light is c. So he came up with a model that is a lot of fun to teach. Typically, it takes me a lecture and a half to teach that model. But briefly, because we only have few minutes, the model involved a wave, which like thermodynamics, we skip for physics 111 and 112. And from the equation of wave, you can get the speed, how fast the wave travel. And then if you invoke Faraday's law, Gauss's law of magnetism, Gauss's law of electricity, Ampere's law, Lenz's law, you end up with the speed here, c. Okay. All right, so I will be remiss if I don't tell you, and this is a fair game for the exam. I know I just say we skip wave. What I mean by skipping wave is a rigorous study of wave. But I want to share, I want you to know at least a few things about wave. First, there are two types of wave. What is one? There are two types of wave. It's on the lecture. Is it? One is longitudinal wave. So the reason why you can hear me is because my lung or my, what do you call that thing? Basically, I perturb air and the wave travels along the medium through the compression and expansion of air and reach your eardrum. So sound wave is an example of a longitudinal wave. Okay. So the amplitude is the compression and expansion of the medium. The other one is, I think I have some demos here. Sorry. So this is what I meant by longitudinal wave and transverse wave. The other one, the amplitude goes up and down, perpendicular from the axis. Any question? Let's discuss what Maxwell did on Friday, and we can do some iClicker question, not a clicker question. I can do some. We can continue using this equation. So using the equation of wave, turns out that the speed of light, Maxwell did this before anyone measure the speed of light. Well, no, that's not true, because all Romer measure the speed of light. But basically, from his theory, he hypothesized, his conjecture is that the speed of light is 1 over square root of mu naught and epsilon naught. And this happened to be close enough to the speed that Romer measured. Right? So if you are in his position, I'm sure you would be very excited. But does he prove that his derivation is correct? Is it a good proof that his derivation is correct? So you build a model, the output of your model is the same as measurement. Is that good enough? You think good enough? Why? You nodded. So let's say, you measure the speed of chicken and I also run at the same speed. It doesn't mean that I'm a chicken, right? It just means that we run at the same speed. So, but that's what he did. It's, let me erase this whiteboard. So C is 1 over square root of epsilon 0 and mu 0 mu naught. So this one is C is equal to 1 over. Anyone still remember what that epsilon naught is? Huh? Okay, so this is how I like to remember it. 1 over, oh, it's there. Okay. And this is like 9 times 10 to the 9th. And I know nobody likes to write units, but at the stage of your career, you have to use units. If you are as old as me, you can write units in your head. So this is K. So epsilon naught is basically equal to 4 pi times 9 times 10 to the 9. And then mu naught divided by 4 pi. Mu naught is basically 4 pi times 10 to the minus 7. Okay. And then, because we know what mu naught and epsilon naught is, then we can calculate the speed of light. So 1 over square root of mu naught times epsilon naught. Sorry, I made a mistake here. Every year I made a mistake. This is why I want to do it right now. Because, so epsilon naught is 1 over 4 pi, right, times 9 times 10 to the 9. Okay. So I'm not joking when I say every year I made mistake on this slide. All right. So so this one is equal to 1 over square root of mu naught is so basically 4 pi times 9 times 10 to the 9th. Mu naught is 4 pi times 10 to the minus 7th. 4 pi cancel. This one equal to 1 over square root of 9. And then this one is 10 to the minus 7 minus 10 to the minus 7, 10 to the minus 7 minus 9 is minus 16. And this one is equal to 3 times 10 to the 8th. So this is what the great Maxwell did. Okay. And we will discuss electromagnetic wave more on Friday. Our demo team gave me a toy today, and let's see if I can make it work. So I think I have to turn off the mirror. So right now this is my cell phone. So basically the question is, unfortunately, it's no longer connected to my Apple TV. But basically the question is different lights. There are many electromagnetic waves in life, right? What is one example? Can anyone give me some examples of electromagnetic waves? No? Infrared or the lights from light bulb. Those are a good example of electromagnetic wave. What else? Did you eat breakfast this morning? No. Microwave. Microwaves is another example, and also the communication between my cell phone to Apple TV is also through a microwave. And one thing that if you don't want me to point this to you, you need to let me know right now. I'm gonna point this camera to you. So one thing that differentiates between these waves is one of them is the wavelength, and we will talk more about the wavelength and wave. So this is an IR camera. It captures the body temperature, and there are some materials that absorb certain wavelengths, but not another wavelength. So maybe you can, if you can hold this thing. So this Pyrex, from what people told me, it absorbs infrared. So just put it on, like, yeah, try to hide, yeah. So look at that. So because the Pyrex absorb infrared, his face disappears. Try this. And there are things that are not visible. Try to hide behind that thing. Thank you. Yeah, so wait, why there is this? My finger, I see. Good, thank you. So, okay. And another nice thing, so that's, thank you for, what's your name? Arman, okay, thank you, Arman. Another thing, there are many properties of wave. We will basically discuss wave for the rest of the semester. The reason why people, like, you can hear me because wave can bounce and travel to your eardrum. If I throw a ball only, let's say to the wall, only a small part of the class can catch it. But waves, because it diffract, it reflect, the whole class can hear what I say. So one thing is that I was told that your body temperature, the name is black body radiation, produce wave, and it bounces to the whiteboard. And when I point the camera, I'm pointing the camera to the whiteboard, not to you. Okay? Then it looks interesting like that. All right? Any question? So basically, we study about inductance, electromagnetic waves, and we will continue our discussion about electromagnetic waves on Friday. Have a nice Wednesday. Okay, what's up? We can discuss, but there are still 10 people who haven't